Many of the reactions in water require a method of titration to determine a component. So we're going to see a fair amount of titrations once we're talking about water. So in this problem, we are asked to find the chemical oxygen demand in a sample of water. So we are given in the problem that our water sample is 50 milliliters. Okay, so this 50 milliliters, for example, we have in some sort of a beaker, 50 milliliters, and we are going to titrate this with, in the problem, it was potassium chromate. So what this means is we usually have an instrument called a burette. So we'll kind of draw this here, and it gives us very precise volumes of liquid. So in a titration, we are looking for a color change to let us know we've reached the end point. So depending on the type of reaction you have, the endpoint can mean a few different things. So for example, the most common we have is an acid and base, where we use an indicator that will change color. So indicators are sensitive to pH. Okay, so above a certain pH, they would be one color, and below that pH, they would be a different color. So we have all different kinds of ranges that we use to look at an acid-base reaction. So if you're looking for something to change colors at, say, a higher pH, you would use something like phenolphthalein. If you were looking for something to change colors at a lower pH, you could use something like methyl orange. Okay, so what happens then when we get that sort of color change? This means that moles of base have reacted and equal the moles of acid. So we have neutralized. Okay, so the acid and base have essentially canceled each other out. So our end point, or our color change, is when our acid and our base have equal moles. So what we're seeing in this one with our water sample in this redox reaction, so in a redox reaction, we are dealing with electrons transferred. And so electrons are being transferred between species, so our oxidized species and our reduced species. So our endpoint is when moles of electrons oxidized equals moles of electrons reduced. Okay, so when all electrons have left the oxidized species and they have gone into the reduction and caused that reduction to happen there. So our endpoint deals in moles of oxidized and moles of reduced. So we use permanganate. So in this example, potassium permanganate, but it could be sodium permanganate because it is a pretty, chromate. Chromate and permanganates are both used quite often because they have a very vivid color associated with them. So you can get your endpoint just by looking at the color. So for example, dichromates are very bright yellow. So as the titration is happening, you would see that yellow color. So this would be, nice and colored and yellow in here. When those drops hit the solution, the color goes away. But as soon as you've reached this end point, that yellow color would stay in solution here, and you know you've reached your end point. Okay, so in our problem here, we are doing this nice titration, and it told us we have a K2 Cr2O7. And of this, in our burette here, we have a concentration of 0.05 0.50 molar. And to complete this titration or get that nice color change, it only required 5.5 milliliters to do that. Okay, so let's take a look at the math associated with this here. Okay, so let's write it out. So we are going to need to look at sort of moles of things that are happening here. So in order to get moles, we have a volume and we have a concentration. So to get moles, using a volume and concentration, moles equals molarity times volume in liters. Okay, so that 5.5 milliliters is 0.0055 liters. Okay, so we're going to do some conversions here. So molarity times volume. So I have my volume here, so I'm going to multiply that by the molarity. So that's 0.050 moles of K2Cr2O7 for every 1 liter. So molarity is moles per liter. And so our liters cancel out. So in this redox reaction that we have here, if we take a look at what's happening in the process, we want to relate our electrons to what's happening in the process. Okay, so if we look at that, all right, so if we look at that half reaction, it was Cr2O7, 2 minus, plus 14H plus 6 electrons. And then we get 2Cr3 plus 7H2O. Okay, so if we look at what we have going on here, we want to get moles of electrons, so we're going to use sort of this stoichiometry here. So if we look, we get 6 moles of electrons in this process, so 6 mole of electron for every 1 mole of the chromate ion. So it didn't really matter if it was potassium or sodium. We're just looking for the chromate. So for every 1 mole of Cr2O7, 2 minus. Okay, or actually we can put our K2 there. Okay, so but for this, even though this is sort of what's happening in our oxygen demand calculation, hence the name, oxygen in here, we're really after what's happening in this process with O2 plus 4H plus 4 electrons to H2O. Okay, so this is the reaction of oxygen that is involved in oxidizing organic material in a body of water. So even though this is nice, we are substituting this in for this reaction here because we can measure this much more quickly and much more easily because it has, again, that nice, beautiful color change. So we're going to link these two through their electrons. So we know that this will have 6 electrons per mole. For this one, we only have 4 electrons per mole of oxygen. So we're going to link those in here where we know for every 4 moles of electrons, we require 1 mole of O2. Okay, so that's essentially swapping from our dichromate to our oxygen, which again, in the name is the chemical oxygen demand. So again, we do want to make that switch to oxygen. So we're going to again use the fact that this one has 6 electrons needed, but this one only needs 4. Okay, so we have that factor of 1.5 in here. Okay, so then the problem asks us to calculate this in milligrams per liter. Okay, so we're just going to go ahead and now that sort of our moles of electrons have canceled, our moles of potassium chromate, we want to convert moles of oxygen to grams, so we're going to use the molar mass. So 32.0 grams of oxygen for every 1 mole of oxygen. Okay, so if we do that, we come up with that we have, okay, so I'm going to go down here, kind of past my reactions, 0.0132 grams of O2. Okay, so if we were to actually look at the mass of oxygen required to oxidize all of this organic material, we would need this many grams. So if we turn this into milligrams, that is 13.2 milligrams. And again, we were going to report this in milligrams per liter. So that's going to be 13.2 milligrams. We're going to take that volume of water, that 50 milliliters, and turn that into liters, 0.0500 liters. And when we solve, we get 264 milligrams per liter. Okay, so that is the oxygen demand for this particular water sample, wherever we happen to get it from. Okay, so that's how we do this calculation. Again, what's sort of important to note, we are dealing a little bit different in electrons. When we are looking at oxidation reduction reactions, at our endpoint, the oxidized electrons equal the reduced electrons. Okay, so that's what happens in a redox titration. You've oxidized one species and you're looking at the electrons involved, and then your reduced species, you're looking at the electrons involved in that as well. Okay, so that was our first problem, practice problem from this chapter. The second problem, we're looking at number 10.13 from the text. So we're going to go ahead and go there. So 10-13. Okay, so this one has a few different fun parts for us. So we are looking at the reduction of nitrate, which is NO3 minus, to nitrite, which is NO2 minus. Okay, so that's the process we're looking at here, converting nitrate to nitrite. Okay, so number one, or part A, we want to write out the half reaction. So we're going to first just write out a half reaction, but then we're going to turn it into a 1 electron half reaction because we're going to start looking at the PE. Okay, so before we even sort of get there, they did tell us this is a reduction reaction, but let's go ahead and verify that by getting our oxidation numbers here. So a couple of rules when determining oxidation numbers, like a couple of things. Oxygen is -2. Okay, unless it is in a peroxide. In a peroxide, so for example, a peroxide is O2 2 minus, the oxygen is -1. Okay. Hydrogen in a compound is always +1. So generally speaking, between your oxygen and your hydrogen, you can figure out pretty much what everything else is. Another sort of thing, if you have a monatomic ion, like for example, zinc 2+, it just equals the charge. Okay? Or if you have that for an anion, like fluoride ion, like F-, the oxidation number is just -1. So charge if it's monatomic. If we're looking for something like a polyatomic, then we're going to use the two sort of species that we know don't really vary, and that's hydrogen and oxygen. Okay, so having said that, we know that oxygen here is -2, and oxygen here is -2. Okay, so we need to figure out, based on the charge and what we know of oxygen, to figure out what the nitrogen is. So the sum of all the oxidation numbers of all of your atoms has to equal the charge of the ion. So for this one, I'm going to say whatever nitrogen is, we'll call it X, plus 3 oxygens that all have a -2 charge has to equal the charge of the ion, which is -1. Okay, so if we solve for that, if we solve for X, in this case, X equals +5. So nitrogen is +5 oxidation number in nitrate. So let's look at nitrite. So same thing, X plus, now we have 2. Again, the oxygen is still -2, and equals -1. So we solve for x in this case, x equals +3. Okay, so nitrogen went from +5 over here to +3. Okay, so to go from +5 to +3, we had to have gained electrons. So gaining electrons is reduction. Okay, so let's write out our sort of reaction here. So we have NO3 minus, and we know this is going to NO2 minus. So I left myself some room to, add all the things I need as I work through. Okay, so in balancing half reactions, the first rule is to balance things that aren't oxygen. So you want to balance everything that's not oxygen or hydrogen. So that's nitrogen here. We have 1 on each side, so we're good to go. So next we want to balance oxygen. So in this half reaction method, we balance oxygen by adding waters. Okay, so we have 3 oxygens here, 2 here. So we need an additional oxygen on this side. So we're going to add 1 water. Okay, so now we have 3. Now we have 1, 2, 3 oxygens over here. Okay, so when we did that, though, we added fun new element hydrogen. So we balance hydrogen in acidic conditions by adding the acid, by adding H+. So since we have 2 hydrogens here, we're going to have 2 H pluses over here. Okay, so that balances our elements: nitrogen, nitrogen, hydrogen, hydrogen, oxygen, oxygen. So now we have to balance our charge. So you can get this one of 2 ways by looking at, we do have a reduction process going on, and it's a 2 electron reduction process, so we can just put our 2 electrons here, or you can do it by balancing the charge. So if we have a -1 charge total on this side, so again, -1 here, and this one's neutral. So all over here we have -1. On this side here we have +1. We need the charges on each side to be equal. So in order to do that, we need an extra set of -2 over here. So our 2 electrons are over here on this side, and now our charge is balanced. These essentially cancel each other out. We have a -1 here and a -1 here. Okay, so this is our balanced half reaction, but when we're doing these PE calculations, we need the 1 electron. So we have 2 electrons here, we have 1. So we're going to solve this by dividing everything through by 2. Okay, so that gives us our 1 electron. So this turns into a super fun 1/2 NO3 minus. This turns into just H plus. Our arrow, here we have the 1/2 NO2 minus and 1/2 H2O. So here is our half reaction with our 1 electron, where again, we did introduce those fun fractions of 1/2. Okay, so that's part A. See part B. Given that for this reaction, so we're on to part B, given for this reaction that E0 equals 0.881 volts, we want to find PE0. Okay, so this is the standard, so this naught, we call it, is the reduction potential for standard conditions. So standard conditions means that your concentrations are all 1 mole per liter. If you have a gas, your partial pressures are 1 atmosphere, and your temperature is occurring at 25 degrees Celsius. Okay, so for our PE0, we have a formula that we use for that, which is our E0 divided by 0.0591. So for our case here, we're going to put in our 0.881 divided by 0.0591, and we get 14.9. So under standard conditions, we would expect the PE of this to be 14.9. Okay, so that's not terrible. There we go. So now we're on to part C. Okay, part C. From your answers, part A, deduce the expression relating PE to PE0 and the ion concentrations. Okay, so PE is equal to PE0 plus excuse me, minus, so we'll go plus negative, log of K, where K is our equilibrium constant that relates our concentrations of products to reactants. So we're going to need this half reaction up here to do this. Okay, so this is simple enough. Let's work on K. So K is essentially you're going to do your products raised to their coefficient, I'll call it N, divided by your reactants. Raised to their coefficient, we'll call it M. Okay, so for us, in our case here, let's look at our products. Okay, so water is a liquid. So in our K, solids and liquids do not appear in there. So they don't have a concentration and they don't have a pressure. So water is not going to be involved. So our only thing we're going to have is this here. So we're going to have our concentration of NO2 minus raised to its coefficient, which is 1/2. Okay, so that's the only thing we have for products, for our reactants. And we're not going to include the electron. We're just going to have our NO3 minus and our H plus. So H plus, so its coefficient was a 1, so we get to keep the 1 there. And then 1/2 for the NO3, so concentration NO3 minus to the power of 1/2. So that is our expression for K. So now we can plug that in here. Okay, so PE equals PE naught minus log, excuse me, NO2 minus to the 1/2 over H plus and NO3 minus to the 1/2. Okay, so that's what we have so far. So now we're going to do a little sort of rearranging of things to kind of clean this up as much as we can. Okay, so PE equals, I can substitute in my PE naught, which is my 14.9. And now I'm going to try to clean this up a little bit. So I'm going to kind of distribute my log here. So I'm going to take log of this, and I want to keep this stuff together because it has the same coefficient. And it's something that, you know, I'm solving for in this equation. I want to know the ratio of these two things. Okay, so if you have a negative log of something that's in the denominator, that turns into a positive. So this will be plus log of H plus. Okay, so that's nice. So we get to bring that out. And then this will have minus the log of, we left these other things in here. So NO2 minus to the 1/2 and NO3 minus to the 1/2. Okay, so I can clean this up a little bit more. And so pH, if you recall, here we'll kind of go sidebar. pH is the negative log of H plus. Okay, so the only difference between this and this is the minus sign, so we can use that. So we get PE equals 14.9. Okay, so we're going to put the minus sign there, minus the pH. And here, because these coefficients are the same, I can bring these out as a multiplier. Okay, so bring those out. We get minus 1/2 log of NO2 minus over NO3 minus. Okay, and that is really the best we can do. Okay, we pulled our hydrogen out to get our pH. Those concentrations of NO2 minus and NO3 minus, we don't know. And they didn't give us that in the problem. So this is essentially as far as we can go for this part here. Okay, so that was part C. Let's move on to part D. Flip this over. Okay, so for part D, we are asked, for your results in C, obtain an equation relating PE and pH under which the ratio of nitrate, so this is part D, and in this they told us our ratio of nitrate to nitrite is 100 to 1. So for every 100 of these, we have 1 of these. Okay, so we're going to plug this into our formula from above, and we're going to solve, and we're going to get the relationship between PE and pH. Okay, so let's start plugging in. PE equals 14.9 minus pH minus 1/2. Pause. Okay, so that howling dog was Pilgrim, and he says hi. So to continue with our problem, so substituting in, so when we get here, we have our log of NO2 over NO3. So they told us it's 1 to 100. So this is going to be 1, and down here will be 100. So we're just putting that nice ratio in there. Okay, so now we're just going to work through and solve what we can. So PE equals 14.9, subtract our pH, subtract 1/2. Okay, so now we're going to do the log of 1 over 100, which if we do that, it gives us -2. Okay, so then we get PE equals 14.9, subtract pH, and we have -1/2 times -2, so we get a +1. So if we combine, we get PE equals 15.9 minus pH. So now we have an expression relating PE and pH for this particular ratio of NO3 minus to NO2 minus. Okay, so our very last part from our results in part C, so our expression, we want to find our ratio of nitrite to nitrate. So we're looking for NO2 minus over NO3 minus when PE is 12 and pH is 5. Okay, so we're going to just, again, substitute into our expression. So this time we know PE, so we'll put that in. So we know that 12 equals 14.9, subtract pH, which they've given us, is 5. Subtract 1/2 log of NO2 minus over NO3 minus. Okay, so that's what our expression looks like. Just start combining terms as we can. So 12 equals, so first thing we can do is subtract here to get 9.9. Again, we'll minus 1/2 log NO2 minus over NO3 minus. Okay, so then we can subtract the 9.9 over. So we do that, we get 2.1 equals -1/2 log NO2 minus over NO3 minus. Okay, so again, working towards this, we can multiply each side by -2. So multiply each side by -2. You get -4.2 equals log NO2 minus over NO3 minus. Okay, so now we've essentially eliminated everything on this side of the expression except for our log. So to get rid of this log and just isolate our sort of variable here, we need to do the anti-log for both sides, which is raising each side to the power of 10. So 10 raised to the power. When we do that, these cancel each other out, and we're just left with NO2 minus over NO3 minus. Okay, so those cancel each other out. So I just need to figure out what 10 raised to the power of -4.2 is. So if I punch that in my calculator, I get 6.3 times 10 to the -5. Okay, so this is my ratio of nitrite to nitrate. Okay, so this is a very small number, so, 0.40, so 0.000063. So which tells us that the denominator is very, very small. Excuse me, yes, the denominator, sorry, reverse that. the denominator is a lot larger than the numerator. So our concentration of nitrate is much larger than nitrite. So whatever this sample of water is, clearly it has the conditions to where it's sort of favoring the more oxidized state, that oxidation number of +5 as opposed to the oxidation number of +3. So wherever it is, there's electrons able to fully oxidize that nitrate down to the +5 again. And we see that with this low value. If this would be a larger value, like for example 100, then that implies that this is much larger than this, and it's favoring this species of nitrogen, meaning the less oxidized species. So it depends on, again, hopefully we've gathered from kind of working through this chapter, it depends on the conditions of a body of water, how oxidized a species will get. So if there's plenty of things to oxidize, then we can get this species here. But if there's not many things out there that can participate in redox reactions in this way, we would get something more like this as being the dominant species.